Hello, my name is IMosqueda, and I'm presenting my senior project of the future of sustainable energy. So, when I started out looking for an internship to start off this project, I knew I was really interested in science, math, the whole STEM field in general. So I knew that I wanted to explore that further because I'm really interested in pursuing a career in my future where I can take knowledge from those fields and apply them to solve real world problems. And I've always wanted to kind of choose some problem space that is really significant, where I can really impact a lot of people's lives. And I've been pretty passionate about sustainability, environmentalism for a few years now, after I was tasked with reading the book Cradle to Cradle in the 11th grade engineering class, which I know half the people in the class didn't read, but I did, and it was amazing. It's a manifesto, essentially, of what we as humans need to do to basically stop damaging the earth that we live on, because eventually it's just going to crumble and we won't be able to use it for anything. And so I decided that that was a specific area that I wanted to kind of pursue. And so where I ended up was at the UVA chemistry department. This was taken on a rainy day, that's why I'm wearing that thing that looks like a trash bag, but it's a raincoat. And so it was at the chemistry department. And here's the front of the chemistry building. The first day that I was there, it was pretty cool. There was an exhibit type thing about women in STEM. That was pretty cool. So my internship mentor is Dr. Jiong Jang. He's a postdoctoral researcher in another Dr. Jang's lab, Dr. Sen Jang, who runs the lab. But Dr. Jiong Jang, who I know as Jerry, that's how he introduced himself to me. I guess that's his nickname. He's a postdoctoral researcher there. And here he is pictured in the lab in front of this setup, which is the primary setup of the lab. And here, this lab, they're focused on synthesizing nanoparticles that act as catalysts in hydrogen fuel cells. And so here is a close-up picture of the whole setup they have. And it's fairly complicated, but where it all happens essentially is in these little vials or beaker type things. And up here are two gas tubes. You might not be able to make out two. There are two right there. And one of them connects to these and pumps nitrogen into them, nitrogen air. And another one is like a vacuum tube. It sucks out of it. And that's essentially just to remove any contaminants from the system. Because in this process, which was the process that was going on the first day that I went into the lab, Dr. Jang was preparing a chemical precursor to making titanium nanoparticles. And this particular reaction wasn't very sensitive to outside conditions, but the reaction the next day that this precursor was going to be used for is extremely sensitive, and all impurities had to be removed. And so it's closely monitored as well. Here's the pressure. These monitor temperature, and that's a thing of liquid nitrogen, which is really cool. All the water, moisture, other small bits of dust or whatever get sucked in there and get frozen and then get sucked away from the system. And so here's just a close-up. These are very oddly shaped, like flasks. So instead of just heating it on a hot plate, they had to be wrapped in heating tape, which was then wrapped in aluminum foil to reduce heat loss into the air. And here's just another close-up of these special flasks that were used for this system. It's a very odd shape. It reminds me kind of like the shape of a human heart, and it has all the things coming out of it. Because for these systems, two of the tubes always have to be used to be pumping air in and sucking air out. And then one of them is to actually pour whatever you want to pour in there. And then this orange thing right here, it's like a rubber membrane, so that when you want to extract the material out of the flask, you don't have to break the vacuum. You just insert a syringe and then take whatever you need out, and then pull it out, and then it'll close back up. So it was a really interesting piece of technology. And so here is the setup on the second day that I came into the lab. So it's essentially the same setup as the first day, but there are different conditions inside of the flasks. So as you can see, they're not wrapped in heating tape or any of that, and they're not connected by tubes. They're only connected by this one bulb-looking thing, which is just the vacuum. And what happened essentially was the chemical precursor from the first day, which was titanium oxide, was injected into these flasks, which only contained oleic acid. And then a very, very rapid reaction occurred, very rapid and very endothermic reaction occurred, in which the particles were basically almost instantly synthesized. So when he injected it, it instantly turned from a yellowish color to that purple color you see there, and a bunch of like little mist came up, but it got sucked away. And then we couldn't feel it because it's behind glass, but the temperature readings spiked way down. So it was a really cool reaction to watch. And then this solution, although it contains the nanoparticles, to be able to be used, they have to be separated from the solution. So they were taken out with the syringe, as I explained earlier, and put into these tubes. And then they were going to be centrifuged, so they had to be balanced in weight because they were going to be placed on different sides of centrifuges. So it has to be balanced. And so he added a isopropyl alcohol, which basically is just, he added that because that's a liquid that won't react with any of the reagents that are already present in the tube, and it just balances out the weight. And so then they were put in this really cool centrifuge at 10,000 revolutions per minute for 15 minutes. So since the nanoparticles are really, really, really small, and they don't weigh very much, this had to be spun a whole lot really, really quickly. And it was really cool because it wasn't really that loud. This thing was really quiet because all the centrifuges I've experienced with personally are kind of, I guess, older, a little clunkier, and they kind of shake around, really old. They had like state-of-the-art technology here, and it was really cool to be able to witness that. And to be able to see the final product, which would be something that could be used in very practical applications. And so on my third and final day, I didn't actually go into the lab. I went into more of a classroom setting where all of the graduate researchers and both Dr. Zhang's, Dr. Sen Zhang, who runs the lab, was actually not physically present. He was out of town doing a conference on the research that occurs in this lab. So he had to attend via a video chat, but he was there. And so essentially what they did was have a literature review meeting, which is just when they cycle through different researchers every time they do one of these meetings, which is about once a month. And that person chooses a scientific report, a paper, that relates to things they're doing in their lab. They read it thoroughly, and then they give a presentation to all of the other researchers about what's in that paper. And then everybody just kind of bounces ideas off of each other about how those ideas can be implemented in their lab, how they can change their own research to make it more efficient, to see what other kinds of new things they can do. And so this day, a graduate researcher was presenting, and the two Dr. Zhangs, the two people, with their PhDs, were the ones that were asking a lot of questions, trying to figure out the specifics. And what they were looking at in this paper, kind of illustrated here, is just more of a linear process. So the process that happened in my first 2 days of the lab was kind of like prepare the precursor, then move it over to this other system. But what they were talking about here was more of a continuous reaction that occurs in one system that's just kind of physically separated by filters and all that kind of stuff to reach the same end goal of creating nanoparticle catalysts. And so at first I was just kind of like, oh, well, they're just reading some paper to look at the ideas, whatever it is. They're just kind of looking at what other people are doing. But they were actually really interested in what this person was doing because they are looking at really similar stuff and are seeing if they can apply these kinds of things into their own research. Because they're always trying to look at what is more efficient. Because the ultimate goal of this research group is to increase the efficiency of hydrogen fuel cells. And so another part of my internship was going to the Rappahannock Electric Cooperative to kind of get a different perspective on energy. Because in the lab, I was kind of looking at state-of-the-art, cutting-edge research about new technology that isn't really implemented. It's just kind of being thought about, experimented on, things like that. But here at Rappahannock Electric Cooperative, I was able to talk to some engineers there and see currently the kind of infrastructure and the type of energy that people are using now. And so on my left here is Mr. John Arp, the Director of System Planning and Engineering Design at the Rappahannock Electric Cooperative. And on my right is Mr. Sam Wilson, Director of the Utility Engineering. So I talked to Mr. Arp, and he does more of like looking at the overall infrastructure of REC and how they can plan ahead for like population growth. One of the big examples he used was Ruckersville, because I told him I was from Ruckersville, and we're experiencing a lot of population growth, and he looks at what they're going to have to do in the future to accommodate for all of that energy, and what they have to do now to make sure that it's running as smoothly as possible. And then Mr. Sam Wilson is the one that actually takes care of the problems. He actually goes out and fixes energy lines and plants and things like that. And I got to visit a substation up in Fredericksburg near their office. Slab Town substation is a substation I got to visit. Here's a small transformer, and this was kind of larger substation, so they also had a larger transformer. And I got to ask a lot of questions. I was with Mr. Sam Wilson, the utility engineer, and it was really interesting to really get to know what was inside of all this stuff, because I have before this I had a general idea of what happens. They get the electricity, it's direct current, they change it to alternating, that goes to our house, whatever. But all of the technology that goes into it, the like complex process, and how long it's taken for firms and engineers to kind of narrow it down into a really efficient process is really interesting. And it also raises questions about like just suddenly transitioning to some other form of energy, how that would affect how we have to engineer other systems to do the same thing. And so my community service, I was also kind of focused on sustainable energy, but in a more education way. So my community service mentor was Mr. Christopher Royer, a 8th grade science teacher at William Monroe Middle School. And I partnered with him, and I came into his classes, and I taught for 2 days. I came into his class for 2 days. And the first day I gave sort of just a lecture presentation on sustainable energy, the science behind it, reasons that humans should transition to sustainable energy. But then on the second day was when we built solar cars, and that was what was really fun. That's what the kids actually really liked, and I really enjoyed. And so we split up every class into 2 teams who had to design solar cars out of a kit that was essentially just all the parts they needed and a solar panel and a motor. And so unfortunately, the day that I went in there for that activity was kind of like an overcast day. So the first class that came in, we actually had to end up using a light bulb, which was really not very powerful. The car only barely moved when we had the light bulb, but we had some sunlight come and go. So when we got the opportunity, we would go outside, and unfortunately, when we did get the opportunity to go outside and actually use the sun, it was really, really exciting. So no one remembered to take pictures. So I only have a picture of me using a measly light stick to power a solar-powered car. But Mr. Royer and I did use this kind of as a teaching opportunity, because that's what is one of the biggest shortcomings of solar energy. If it's cloudy, overcast, you can't really use it. And so, we went on with it, and we did eventually get them out in the sun. They were really fast. And after this community service, I conducted a survey of the students. And one of the most important questions in the survey was, are you more interested in science after this activity? Just science in general. And although a lot of people seem to be unsure, there's also a fairly amount of people that said yes, like a hard yes. So that's pretty good. So There weren't many that said no. A lot of them said yes. So I think that I could say that I mostly achieved my goal of inspiring younger students to not necessarily pursue this field as like a career, but to pursue knowledge in this field in hopes that they might become more interested and apply it to solve what I think is one of the more pressing problems that society is facing now and will face in the near future. And so for my research, I decided, like all other aspects of this project, to focus on the energy aspect of sustainability. And so here, we're just really looking at kind of the problem space that I chose. So this is energy usage in the world, and only a very, very small portion is renewable energy. And over here, you can see it split up into what kinds of renewable energy we have. And if you look at this is the potential energy that the world holds for us. And on the right, no, that's your left, this side, that's the annual potential of renewable sources of energy. And then over here is just how much we have left of all of these fossil fuels. So just looking at solar, that's already way more just per year than we have remaining at all of fossil fuels. So obviously there's a discrepancy between what we're using the most and what we actually have the most of. And that's primarily due to gaps in technology and in our essentially stubbornness to move on from fossil fuels because they're the most economically viable right now. They're the easiest to obtain, cheapest to obtain, easiest to use, and all of our infrastructure is built around that. And so for my solution, well, my thesis question was, what is the best solution to transition away from fossil fuels, and how can we most effectively do that? And so what I chose as the answer to that is hydrogen fuel cells. And here's a diagram of a proton exchange membrane hydrogen fuel cell. And essentially, hydrogen gas comes in, it's broken up into two hydrogen atoms with the electrons going off. And the electrons go up here, travel through here, and then go through a motor, creating electricity, doing all the work we need, and then traveling back to the other side of the fuel cell. And then the hydrogen nuclei, which are just protons, travel across the proton exchange membrane, hence the name. And then they meet back up on the other side, and then they react with oxygen gas, which is just drawn from the air, and then they form just water. So the only physical byproduct of these fuel cells is water. And that's really good because it doesn't create any greenhouse gases, doesn't contribute to global warming. And so that technology is great and all, but we also kind of have to look at how you have to implement it, because you can't just throw money at it and then hope it kind of resolves itself. We have to implement policy that will kind of meet at the crossroads of the economy and environmentalism. Because what's always best for the environment isn't always what's the easiest for the economy or the most viable for the economy. And so for this, I came up with my comprehensive fuel cell plan, which I wouldn't really put it past myself to call it comprehensive just because it sounds good, but I think it actually is fairly comprehensive. So it starts at a policy, which is essentially the most fundamental, besides funding, which we'll get back to because it cycles back around. But at policy level, one of the biggest things is to increase funding to research more fuel cells, to increase their efficiency, how easily they can be transported, and how easily they can be produced. And this will increase the economic viability of fuel cells, make them better competitors for fossil fuels. So we can transition away from fossil fuels and towards more sustainable energy usage. And then on the other side, we have just policies that economically strengthen fuel cells, essentially make fuel cells just easier for people to use, cheaper, and make it more on the level of fossil fuels that exist right now. And so two of these are really important because they're two policies that actually create funding for everything else that we're doing. And so that would be increased taxes on all fossil fuels and increased fines for environmental regulation breaches, and have those be strictly And then these other three would just help make fuel cells a more viable option for individuals and firms around the country. And these are all things that have been already tried out and shown to be successful at the state level, like in California and Connecticut, which are two of the leaders in fuel cell policy in the United States. They have tax incentives for businesses and just businesses that use fuel cells. And then there are rebates, loans, grants, and special financing available. Rebates are primarily for hydrogen fuel cell vehicles. California is currently the only state that has hydrogen fuel cell vehicles on the market, and they do offer rebates of up to $5,000 to purchase those vehicles. Although Connecticut is also planning on doing that very soon in 2018 or 2019. And going in with the loans, grants, and financing is a sustainable energy central bank. So the state of New York has a green bank worth $1 million, which simply loans out at special lower rates for businesses looking to go into alternative energy, or just businesses who want to use it. They're just businesses that aren't really involved in energy, but they're using that energy. And all of these will increase the economic viability, which is the ultimate goal, because we want to make not only a technological transition to fuel cells, but also an economic transition that will result in the least loss of money to the economy in general. And so my advice for future seniors is just to do whatever, because you don't know what you're interested in until you try it. Everyone else saying, choose something you're interested in. But really, the only experience we have with most stuff in high school is like reading about it, and that's never actually what things are like, I think. So just do whatever, and if you don't like it, that's too bad. But you won't do it again. And if you do like it, then you can continue doing that. And so my future plans, I am attending the Massachusetts Institute of Technology this fall, and I'm planning on majoring in either chemical engineering or material science and engineering, which both have large applications in environmental areas of work, because material science is like focused on kind of batteries, fuel, stuff like that, and chemical engineering is focused on how we make materials, which is a big part of sustainability, although it's not as directly involved with energy, still sustainable. So thank you, and are there any questions?
Since Annalisa talked about like women not, like girls not being as interested in STEM, I was wondering if when you were in the classroom, if you noticed that like the boys in the class were more interested in the activity than the girls, or if you didn't really see that difference.
So when I was in the third day when they were presenting stuff, I was never really in like a classroom. So it was just all the researchers, like the graduate students and the professors. And so it was about half and half, girls and boys in there. And all of the students were kind of like, kind of chilling, because their doctoral, Dr. Zhang and Dr. Zhang, two people with their PhDs, were the ones talking the most. So the students all just kind of stayed out of the way and only answered questions when they were directly addressed. So I can't really comment on like disparity between the two genders, but just on a representational basis, it was about half and half of us in that. But it also wasn't directly engineering; it was just science. Yes.
So I don't know if you thought about the Atlantic Coast Pipeline at all in the course of doing this project, but one of the arguments is it's a natural gas pipeline that's going to be coming through a lot of Virginia. One of the arguments in favor of it is that while we're moving from fossil fuels to renewable energy, natural gas is cleaner than coal, so it makes sense to go ahead and build this pipeline for Virginia. I mean, you talked a little bit about that, how difficult it would be to just instantaneously move to completely renewable energies. And I was just wondering if you had any thoughts on natural gas pipelines or Keystone or the Atlantic Coast.
Yeah, actually, so natural gas, it's much cleaner than all the other fossil fuels, like you pointed out, and it was referenced in a lot of the sources I looked at as sort of kind of a bridge, because it's cleaner, and it's also a gas. So infrastructure that would be used to transport natural gas would also be much more, it would be much easier to turn that infrastructure into something that could be transporting hydrogen gas or hydrogen fuel cells if that were to become a more popular energy source. So yeah, I do agree with that statement that if implemented properly in a way that does not um, endanger ecosystems more than is reasonable, that's a good transition away from the traditional fossil fuels like coal and gasoline stuff to like hydrogen fuel cells and more renewable sources of energy.
So you're convinced that, I mean, you're willing to have the government make a um, choice needed that says, we know that this is the solution. Is that right? The last time I went, and this is like, well, over 10 years ago, I went down this road with a big, and at the time it was something like $2 trillion to replace the infrastructure that is represented just by the gas pumps and everything that is around the United States. So that seems like a big bet to me if it doesn't work.
Yeah, so that's definitely a very reasonable concern. So I guess what I would say is that this focus is more on what we want to, what point we want to be at in other areas when fossil fuels just run out and we don't have any more. So like oil is projected to run out before 2100 from the sources I looked at. Coal is last, well, it's projected
They've
to
been
last
saying
much
that
longer.
for about 200 years. So,
Yeah, so
yeah.
although we can't really look at, I guess, accurately when it will run out, it will at some point. So I guess I would say this is more so something to be really, really long-term transition to once we're at the point when we actually don't have any of it left, even if we can't tell when that point is right now. So I guess it's really difficult to judge how fast this would have to move and at what point we would have to be at in certain points in time. But for now, while we still have cheap available fossil fuels, just transitioning enough that we're decreasing our impact on the environment. So not entirely, transitioning the entire economy right now or before fossil fuels run out.
It's a great solution. It's just, and I know you had to come up with a scheme and everything had to, this sort of a mandate included in this, but I would just, I guess I would say, be skeptical about the government's wisdom in mandating choices